For years, Jupiter felt like a planet we were finally starting to get under control. We could not land on it, but we could model it. We thought we understood its layers, its storms, and the rough shape of what was happening deep inside. Then NASA sent a spacecraft closer than ever before, and Jupiter stopped cooperating. The discovery was supposed to simplify things. Instead, it did the opposite. The more data came back, the less Jupiter looked like a planet with a clear structure and predictable behavior. Measurements that should have lined up did not. Features that were expected to be shallow turned out to run far deeper. Even basic assumptions about how the planet is mixed inside started to fall apart. This is the part that makes scientists uneasy. Not because something broke, but because the answers are no longer clean. When a discovery gets worse in science, it usually means the system you are studying is more complex than your best models can handle. Jupiter is doing exactly that. What NASA found did not just challenge a few details. It raised questions about how the largest planet in the solar system actually works, and whether the rules we use to understand giant planets even apply. The mission revealed something real, but it also revealed how much we still do not know. The headline discovery came from how close NASA managed to get. For the first time, scientists were measuring Jupiter's gravity and magnetic field in extreme detail, pass by pass, skimming just above the cloud tops. Those measurements act like a scan of the planet's interior. Tiny changes in gravity reveal how mass is distributed inside. Variations in the magnetic field hint at what is moving, where and how deep it goes. What they expected was a fairly clean picture, a dense core in the center, layers of hydrogen and helium above it. Weather confined mostly to the upper atmosphere. That idea had been around for decades, and it worked well enough on paper. The data did not agree. Instead of a compact core, Jupiter appeared to have a diluted one, stretched out and mixed with surrounding material. The gravity data suggested that the planet's interior is not neatly layered, but partially blended. At the same time, the magnetic field turned out to be lopsided and patchy, stronger in some regions than others, which should not happen if the interior were simple and uniform. Even Jupiter's famous storms played a role. Measurements showed that the jet streams and cloud bands extend far deeper than expected, reaching thousands of kilometers down. That meant the atmosphere is not just a surface feature, it is tied into the planet's internal structure. At first, this looked like a breakthrough. A single mission had rewritten textbooks. Jupiter was bigger, messier, and more dynamic inside than anyone predicted. But that clarity did not last long. As scientists dug deeper into the measurements, the clean story started to unravel. The early models could explain some of the signals, but not all of them at the same time. When researchers adjusted one part of Jupiter to fit the gravity data, the magnetic field stopped making sense. When they tuned the interior to match the magnetic readings, the atmospheric behavior no longer lined up. One major problem was mixing. If Jupiter's interior is partially blended, heat and material should move in predictable ways. But the data suggested uneven regions where material is trapped or moving differently than expected. Some layers seemed stable when they should be turbulent. Others appeared active far deeper than theory allowed. The atmosphere added another layer of confusion. Certain chemical signatures implied deep circulation pulling material up from below. At the same time, other measurements suggested the opposite, that parts of the atmosphere are surprisingly isolated. Both cannot be true in a simple model. Radiation and instrument limits also mattered. Jupiter is an extreme environment, and even small uncertainties in measurements can grow into big disagreements when you are trying to map a planet this massive. That forced scientists to ask an uncomfortable question. Were they seeing new physics inside Jupiter, or the limits of how well we can measure it? Either way, the original discovery no longer felt settled. Instead of pointing toward a clear explanation, it opened multiple paths that did not agree with each other. All of this uncertainty would be easier to deal with if the mission had endless time. It does not. The spacecraft is flying through one of the harshest radiation environments in the solar system. Every close pass slowly damages its electronics. Instruments degrade, data becomes noisier. Engineers can compensate, but only to a point. That matters because the questions raised by the discovery require repeated measurements. Scientists need multiple passes over the same regions at different angles and depths to separate real features from noise. They need time to watch how Jupiter changes. Instead, they are working with a shrinking window. There is also the problem of trajectory. The spacecraft's orbit was designed to sample many parts of the planet, not to hover and recheck specific anomalies over and over. Some of the strangest signals came from regions that may never be measured again in quite the same way. That makes confirmation difficult. Then there is the human side of the data. As the mission stretches on, researchers are forced to choose what to prioritize. Do they focus on refining interior models, or on atmospheric dynamics, or on magnetic field oddities? Each choice leaves something unresolved. This is where the discovery starts to feel worse. Not because it was wrong, but because it may remain incomplete. Jupiter has revealed that it is more complex than expected, and the mission designed to explain it may not have the time or precision needed to finish the job. Jupiter is not just another planet on the list, it is the template. When scientists build models of giant planets both in our solar system and around other stars, Jupiter is the reference point they start from. If Jupiter does not behave the way those models assume, the problem spreads far beyond one mission. For decades, theories of planet formation relied on a fairly simple idea. A solid core forms first, gas piles on top, and the interior settles into layers. That framework shapes how we interpret thousands of exoplanets. A diluted core and a partially mixed interior make that story harder to defend. It suggests that giant planets may stay messy for billions of years, or that violent early events reshape them in ways we did not account for. The depth of Jupiter's weather systems matters too. If atmospheric motion reaches deep into the planet, then surface observations alone cannot tell the full story. That complicates how we read data from distant worlds where we only see cloud tops and light curves. There is also a practical impact. Future missions are planned using assumptions drawn from Jupiter. Navigation, radiation models, and instrument design all depend on how Jupiter behaves internally. If those assumptions are off, future spacecraft may face surprises. So when scientists say this discovery got worse, they do not mean disappointing. They mean disruptive. Jupiter is no longer a clean example that supports existing ideas. It is a stress test, and right now, some of our best theories are failing it. Jupiter did not give NASA the answer it was looking for. It gave something more uncomfortable. A reminder that even the biggest, most studied planet in the solar system can still break our assumptions. The discovery did not collapse. It fractured into pieces that do not fit neatly together yet. That is usually how real progress looks. A simple idea survives until better data arrives, then reality pushes back. Jupiter pushed back hard. Its interior appears blended instead of layered. Its storms reach deeper than theory predicted. Its magnetic field refuses to behave symmetrically. None of that means the mission failed. It means Jupiter is telling a more complicated story than we expected. What makes this moment important is not that something went wrong, but that something deeper was exposed. The models were too tidy. The planet was not. And if Jupiter is this complex, then many of the giant planets we think we understand may be just as messy beneath the surface. The discovery got worse only in the sense that it stopped being comfortable. And in science, that is often where the real learning begins.